Moving on into section 2.2, the infinite square well. And so I thought first it'd be good to kind of back up and just talk about what we're doing overall. So in quantum mechanics, we're going to be very interested, one of the things we're very interested in is bound systems. And so these are interacting quantons where the nature of the interactions keep their relative separation limited. So for instance, like the electron that is in the hydrogen atom is a bound system. All right, so lots of examples: molecules, atoms, subatomic particles work this way, solids work this way. So these are all things that quantum mechanics can help us with. And so to start out, we're going to make some simplifications. So the first thing, we're going to focus on one particle at a time. So we'll be looking at sort of the impact or sort of what one quanton will feel. And so we'll take everything else in the system that might be there and say all the other particles create some potential energy V sub x. And so that's what we'll be doing in quantum mechanics for a little while at least. And we'll assume that the single quanton's mass is so small compared to everything else that it won't change, okay, the field that it's interacting with as it moves around. And so we'll start with pictures kind of like this here. We'll make little diagrams of the potential energy. And so you've done this stuff probably in first year, but not very much. And so I think at first this can be a little bit, it can take a little bit of getting used to. But basically we want to make some potential energy profile kind of like this here. This will be our sort of our standard. And then we'll say, okay, well here's our energy. Now classically, this is kind of so easy, we didn't spend too much time with it, but classically, okay, these red points here are the turning points. And so this region here, if this is the energy of our particle, all right, this energy in here is the classically allowed region. And so if we have some particle with that energy, and assuming there's no friction, this particle would just sort of bounce back and forth. Okay, and if there was friction, it would be losing energy, but whatever you want to do, that's how it would sort of behave classically. And this would be then the classically forbidden. So since the maximum energy is right here, this is basically where its kinetic energy turns zero, and it's all potential energy at that point, and it stops and turns around. And so we're going to look at similar profiles and see basically how the quantum mechanics affects this. All right, and in classical, one important thing is that there's no constraints on the energy. So in this system, I could put my energy sort of anywhere I wanted to, including like up here, and then there would be no classical turning point. And so I can basically do whatever I want. In quantum mechanics, we'll see it's a little bit different. Now, what are we trying to mimic? Well, here is sort of a one-dimensional slice of, say, the potential that you would feel in a hydrogen atom. All right, and so this here would be our proton, and the proton creates a 1 over r potential that would look something kind of like this here. And so for our electron, sort of the lower potential energy would be sort of right here. Again, this is the x-axis, so this would be x equals to 0 where the proton is. And so you'd sort of have the maximum, or your minimum energy would be right there on top of the proton. But what this has is just like that similar profile, it has like a little thing that confines the particle. Okay, so the particle feels a lower energy in here and sort of gets confined in there. If you look at, say, a solid, what a solid, again, it's like a one-dimensional cut of a solid. So here are sort of the nuclei of some solid. All right, if you look at what the electron sort of sees, is again it sees sort of a lower potential sort of right in here, sort of at the point where you're right on top of the nuclei, and sort of higher potentials as you get around. And so if you're an electron, see like right here, again, this is a potential that kind of confines you. Okay, if you have a lot of energy, you could come over here, maybe jump to the other side or something, but there's sort of a barrier there in between, and so you would sort of expect these electrons to be sort of in those spots there. And so this is what we're aiming at, trying to be able to understand. And so we're going to start with some potentials that try to mimic this. And the first potential we're going to start with to try to mimic this is the infinite square well, which we'll see this referred to as a quanton in a box. And this is in some ways very unphysical, because the potential, okay, in this particular system is 0 from 0 to a, and then it's infinity outside of that. So infinity is of course impossible, but there are some systems where basically the potential is so high that you can treat it as being very close to infinity. And so what that means is, again, this is something that confines the particle. Okay, your particle is going to be trapped inside this region. So since there's potential is infinite outside, it's impossible for it to actually go outside. And so this is our first way of, again, trying to mimic these potentials that we have for, say, atoms, and then for, say, one atom. Okay, so it's not perfect, but it's a good starting point. And in actuality, these days, we can actually create systems that are exactly like this. So this is a quantum well. So I work in nanoscience, and so this is something that I deal with often. And so what you do is you make a sandwich of materials. So here we have these two kinds of materials and a little sandwich here. And so here we're talking about something on the order of, hundreds of nanometers or so. So it's a very, very small distance. And the way that these materials are set up is that when we have the electrons stuck in here, all right, so we put the electrons into this gallium arsenide region here, the potential to move sort of out is very high. It's not infinite, but if you sort of drew it, it would be something very high like that. So the particle is confined in this one dimension. And so here a quantum well is an example where you have a pretty much almost exact version of the infinite square well. But for us, it's really, I think, more important for us to use it to sort of, again, learn more about how the Schrödinger equation works and how these confining systems, these bound systems, can work. So let's get down to solving our differential equation. So again, our goal for much of the rest of the semester is going to be to solve the time-independent Schrödinger equation for different potentials. Now, this one's kind of weird. The potential is infinity at some points and then 0 at other points. And basically the way that it works is the places where it's infinity, we don't have to worry about it because the particle will never be there. And so we can take this equation and just look at it for the case when Vx is equal to 0. Which of course makes this much easier. And so we take our equation here like this, the second derivative with respect to x equals here. And now what we tend to do is it just makes life easier to make this a little cleaner. And so we're going to take this and just multiply by negative 2m over h bar squared. Okay. And so over here, of course, what that does is it cancels everything out. And so we have this second derivative dx squared, and that's going to equal over here negative 2m over h bar squared times e times psi. And so it's the same equation as over here, it's just that we sort of rewrote it. Okay, and this is what the textbook does. And then the textbook even takes a bigger step. Okay, and what they do is they call this constant here, all right, this thing here, they call that k squared. Now you might ask, why do they call it k squared and not k? Well, just because when we get the solution, it basically makes more sense, because when you're taking two derivatives, you're going to have two of those factors, and so it's k squared. But you don't really have to call it k squared. And so our equation boils down to this. And this will end up being one of the differential equations that we'll deal with the most. And so it's one that we'll talk about quite a bit. Here's just a quick primer on two of the most common differential equations we'll see not only in quantum mechanics but in physics. And again, we've talked about this a little bit, but a differential equation is some equation that deals with derivatives of a function and then usually the function itself and some constants. And your goal is to find a function that agrees with that equation. And basically, if you find one function that works, or a function that works, you're done. And so differential equations class, they go through and try to come up with different ways to solve these. So there's lots of ways to sort of think about solving these. But here's just with these two how I think about them. So for instance, with this top one here, we're going to find that the solution, okay, is going to be some kind of a wave-like function. So let's just take sine, for instance. If I take two derivatives of this function, sine k of x, I get negative k squared sine k of x, which of course equals negative k squared, which is just a constant, it's the constant in here, times my function of x. And so this equation here, what it's telling us is we want some function where if I take two derivatives of it, I get a negative constant times the function itself. And that happens with the sine. It also happens with the cosine. So in fact, the general solution will be a combination of these. All right? And so it's a wave-like solution, and it basically always curves towards the x-axis. Now over here, we have the sort of similar one, but without the negative sign. And so here, this solution will be exponential-like. And so for instance, if I pick e to the x, or e to the kx. And so again, we want some function where if I take two derivatives, I get the function back times a constant. So if I take two derivatives of this, I'll get k squared e to the kx, which equals k squared times my original function. And in fact, what also would work would negative k squared, and so that would be the general solution for that. If you do that, you get the same thing. Okay, so these are the two, like I said, most common differential equations we come across, and so it'll be helpful for us to sort of almost have the solutions of these memorized. Okay, so back to what we were working on. We took the time-independent Schrodinger equation and got it into this form in the case that we're talking about, our infinite square well. And so as we just talked about, our general solution to this differential equation looks like this here. And so what we throw in are some constants. And generally now what we're going to do, and then you'll do this similarly in other physics classes, is when you're solving a differential equation, you go back and you use like usually boundary conditions to solve for the constants in your equation. So we're going to go through and try to show us how we do that. And so again, so here's our Quanton in a box, and basically our boundary condition is that the wave function must go to 0 at the endpoints. Okay, the wave function must go to 0 because there should be no probability of finding our particle, okay, inside, in this case, this region where the potential is infinity. So we're going to find in quantum mechanics the particle will oftentimes be able to be found just about anywhere, but the one exception we make is when the potential is infinite. And so here we must make the wave function 0 at these boundaries. And so let's go through. So here's a question. So given that our solution is this thing here, again just what I was just talking about, okay, this is our solution, and so the boundary condition is that at 0, this should equal 0. And so if that's true, which one of these should be true? So go ahead and think about this, maybe pause, and we'll talk about it. Okay, so I got here that this should have been b. So let's just go through this. So again, I want this function to equal 0 at x equals to 0. So I say a sine of what's going to be 0, because k times 0 is 0, plus b cosine of 0. And so sine of 0 is 0, so this piece goes away. Cosine of 0 is 1. So I get this a nice equation that says b should equal 0. So in this particular case, with the particular situation we have, all right, even though this is our general solution, okay, in order to make our situation physical, okay, we need this boundary condition to be true. And so what that does is it basically kills out that b. And what that really means is now that our wave function no longer has the sine part, no longer has the cosine part, and only has this sine part. And so now, given that our new wave function is like this, we've gotten rid of the one that had cosines in it. The other boundary condition is that at position A, our wave function should be 0. So what boundary condition, or what condition does this imply? So think about this and we'll talk about it. Okay, so hopefully for this one, now this one is kind of a dirty trick. You may have picked D, but technically if we look at this, so what are we saying now? Well, we want this function to be 0 when a sine of Ka is equal to 0. Now one way to do that is to make a equals to 0, but then we don't have any kind of a function, so that's not very helpful. Another way to do that is to say that the sine term has to be 0. Well, the sine term will be 0 when k times a equals n times pi. Okay, and so what that does is it quantizes k. So k will be equal to n pi over a, and of course here we're saying that n is 1, 2, 3, ... So if you picked D, you were close, you just sort of were forgetting this a here. Okay, and so this is our condition now that quantizes our problem. And so if we write this out then, okay, what we come out with over here is, so this is our wave function. Okay, so for k, I plugged in that value we just got, and so this is our wave function solution. So this is our energy eigenfunction, or whatever else you want to call it. Okay, this is our solution. And then we can kind of do a few things. And so first of all, if you go back to there, that k constant, the way that Griffiths defined it, looks like this here. And so what we can do is now we know that our k equals n pi over a. And so I can take this, and if I solve this for E, I get this right here. And so this is the energy that's associated with this state. So again, this is an energy eigenfunction, which means it has a definite energy. This is the definite energy. Okay, and on the fall 2016 test, we basically did this calculation. Okay, we sort of did it in a sort of a different way. We did it sort of thinking about de Broglie waves, and the energy was this here. And the thing is, if you just correct sort of convert h bar into h, you get the same result. And so this is just a different way to write that energy. But this is the quantized energy. And so that's what this is saying, is this relationship here tells us that this energy has to be quantized. And so if you go through and normalize this wave function, you come out to get this right here. And so this, if I normalize it, then when I integrate, I'll get a total of 1 when I look at that. Okay, so it's good now, I think, to stop and kind of look at our solution. So again, this is our solution for the infinite square well. This is our energy eigenfunction for it. And so this is one equation, but there's an infinite number of these. And so here we've got the first 3. So here's n equals to 1, n equals to 2, n equals to 3. And so the idea here is that we're fitting, okay, different parts of the wave. And so the key is that it has to be 0 at the endpoint, 0 in A. Here I'm fitting half a wavelength. Here I'm fitting a whole wavelength. Here a wavelength and a half, and then it'll keep on going over and over. And so these are the actual wave functions for these particular cases. Okay, and again, if you take psi squared, that gives you an idea of the probability of where you might find the particle. And so there's a couple things about these solutions that'll be true for a lot of solutions that we just want to kind of talk about. So first of all, they're alternately even or odd about the center of the well. So if you look at the center of the well, I'll try to draw it as good as I can right through here. Okay, so this one is even about the center of the well. This one is odd about the center of the well. And then this one over here is again even. Okay, and so for symmetric potentials, which this potential is symmetric, right? It was just 0 from 0 to A. This will always be true. So this can be useful. Remember, because symmetry can be really helpful. The other thing is each successive state has one more node. So we start with 2 nodes, then we have 3 nodes, then we have 4, and each successive state will have more nodes. And this will be a universal aspect of these energy eigenfunctions for bound states. So alternately even or odd about the center of the well, each successive state has one more node. Another thing that we're going to find, and we'll talk a lot about this in class, is that the eigenfunctions will be orthogonal. And what that means is if I take this equation, if I take this here, so if I integrate from 0 to A of the m and the n of these wave functions as the energy eigenfunction, it comes out to be this thing here. Now this is a really weird thing. You maybe not have seen this before, but it basically says that it's equal to 1 when n is equal to m, and it's equal to 0 otherwise. And so what that means is basically when they're equal, this is just a normalization, okay, equation or integral, right? And so it equals 1. When they're not equal, it's going to be a 0. And we're going to find out that this is our definition for these functions to be orthogonal. And finally, they are complete. We talked about this last time. What that means is you'll be able to express any wave function as a linear combination of these energy eigenfunctions. And the next time we're going to spend some time really getting into that. And lastly, I just wanted to address this question. So this is a really common question, I think, which is what does it mean for two functions to be orthogonal? So we mentioned this in Griffiths, and I just mentioned this, and we don't necessarily talk about it. But so what did that mean? Well, for two vectors, okay, to be orthogonal, the way we calculated that is we did something kind of like this here. Okay, suppose I have two vectors, and so that said that AC plus BD equals 0. Well, now what you're doing is a wave function, essentially, like we sort of talked about, you can kind of think about it as an infinitely long vector. Okay, and so what you can kind of think about is imagine if you had an inner product of, say, two really, really long vectors. Okay, so psi m and then psi n, for instance. Okay, and so those vectors were super long, and they sort of, if you do the inner product, you would do kind of like this. So you'd have psi m, the first element, plus psi m, the second element, plus dot, dot, dot. And then you do this inner product with psi n's first element, psi n's second element, dot, 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 like that. Okay, if you took this, what you'd end up with is this really big sum. So psi 1m, I should be careful, we should call these stars. So these are the complex conjugates, times psi n1 plus psi m star 2 times psi n2 plus dot, dot, dot. And so what that would equal is this big sum of psi m, okay, the elements of the ith element star times psi n's ith element, and you'd sum that over I. And basically what we're doing with this integral is you're just taking this and turning this sum here into an integration. So you're making the distance between these elements 0, so there truly are infinitely elements, and you're getting this here. And so the idea is that this is the inner product for functions. Okay, integrating them over all space dx. And if the two functions are orthogonal, it'll end up being 0. And these functions will be, these are our energy eigenfunctions, so they're going to be really important to us, just like our eigenvectors were with our rules of quantum mechanics.